Hello everyone, this is a short video on an introduction to SKLEARN. We will do it in three different notebooks. First one would be just data generation, visualizing the data and training a simple model. The second one would be using validation scores, and the third one would be on the cross validation. I have the code here on the right hand side, and on the left side we have a terminal with a IPython kernel running in it, basically as a scratch pad, so I can explain things a bit easier. Alright, let's jump in. Let me clean that kernel first. Awesome. First things first, we will we will import few modules here. Most of them you already are familiar with, NumPy, Pandas, SymPy, and so on. The IPy widgets is for interaction with button sliders in the Jupyter notebook. We are not using that here, but it's just so you know. Matplotlib for plotting, CM for Matplotlib is for color maps. Seaborn is plotting library that works very well with pandas data frames, and then sklearn and so on. One thing you always need to keep in mind when you're working on a machine learning project is setting the random seed. Reproducibility is a very important key in the success of a machine learning project. And because you're working with a lot of random number generators, you need to really set the seed for the random number generator. In this case, we're doing it for NumPy because this is the one every other module here is using. If you're using other modules that generate random numbers, you need to set the seed for them as well. Let's go ahead and run that. Alright, so the very first thing we'll do is to generate some regression data. We do this with a function called makeRegression from a submodule in sklearn called sklearn.datasets. Basically what you do here is you specify number of samples you want, number of features, and whether how many of these features are actually informative, and so on. Now when you do this, it will give you an X matrix of M samples, or 1000 samples in this case, and four features for values for each row there, and then we'll give you also the Y of the target values that you are doing the regression for. After that, we will pack this data into a pandas data frame. So we'll say a new data frame with data equals X, and columns, we'll set the columns name there. Now this way of specifying a list of names, or a list of anything really, is called the list comprehension, and it is similar. Let me go here on the side here. So if you have a list and you say this would be 0, 1, 2, 3, 4, this would be your list here. You can also define this list in a different way, which would be I for I in range 5, and this will give you the exact same result. The way you define the list this way is more mathematical in a way, but it is also helpful when you try to make a specific relation between the numbers or something. So you can say maybe I squared for I in range 5. So this will give you all the i's squared. In our case here, we are using column names, so we are using f-string. We'll name every column x, and we'll give it an I for I in range, say 5. So when we see columns, it will be x0, x1, x2, x3, x4, and so on. So now we generate our data, we put it in a data frame, we then add the y column for that because this data frame only has x for now. So we'll add the y as well, and then we'll do x dot shape, y dot shape, df dot shape. Always check the shapes of your matrices. Sometimes you will have very long, say, vectors, and if you're not careful with how many data you have there, you might end up multiplying two vectors together and having a matrix. The resulting matrix might be million by million or something, will eat up your RAM, will crash your system, and so on. So always keep an eye on the shapes. It's a good advice. And then we'll see a snippet of what the data frame has after that. So we have the X shape is 1000 samples, 4 features each. The Y shape is 1000 values. And the data frame dot shape is 1000 by 5. We have 4 feature values plus the Y value here because we added Y to the data frame. So next step would be plotting the dataset that we have. So we have SB, this is the Seaborn library I was talking about. It has a function called pairplot which goes across all columns in the data frame and plots them against each other. This will generate a big figure very quickly for you, and it will be much easier to spot any relations between the inputs and the outputs. The way it works, it takes a data frame in a variable called data or an argument called data, and then you can specify the kind to scatter. This would be a scatter plot, and this is actually the default, so you can leave it there. Now when we plot that, okay, so this would be your dataset, and it's like a bird's eye view of the dataset. And what you're actually looking for here is any relationship between the x's and the y. We can see x0 and x1 having some sort of a relationship between x and y. This will actually change if you make, say, this only one informative feature, and this will give you a result like this. X0 and y have almost uh, linear relationship here. So let me start from that. And then we can plot this. Now we have x0, x1, x2. Now you can see why we need to set the seed, because every time it will give you a different data set, even if you change a few things here and there. So yeah, you can also add the, say, the noise factor, which would be, say, the standard deviation of a Gaussian noise applied to the data that you have. Now this data set that we have now is actually pretty much all the features are not really doing anything to the y, but the x1 feature does have some relationship with the y, and this is what interests us here. Okay, so we have our data, we have our plot, we have identified what feature we want to work with. Now let's make a new linear regression model. We import that from sklearn.linear models, and what feature do we have here? We have x0, x1, x2. We need x1. So, and we can take a slice of x and say basically we want all the rows with the columns with the columns x1. So this would be similar to, let's make an x array here equals mp. Let's import numpy first. So now if I say x equals mp dot arrange, say 16 dot reshape 4 by 4. So if we write x, this would be our x here. Now if I say x sub everything and 0, it will give me the very first column, but will return it as a one-dimensional array. It will not return as a column. If I want it as a column, I can take it 0 to 1, like that. It does not include the 1, but it will include the 0 as a column. Now, in our case, we want x1, so we'll take 1 to 2. Like that. Alright, so we have our x's, our y's. Now, again, always check the shape. Now, let's define our machine learning model. Machine learning model here, we'll give it a variable called MDL, and it will take linear regression. That's it. There are different parameters that you can use, but this is something you can explore from the help. Now, to train our machine learning model, we say mdl.fit, and we'll give it the x data and the y data that we want the model to train on. And after the model trains, you can extract the coefficients and the intercept of the model. This would be the slopes and the constant at the in the linear equation, or the coefficients of a polynomial, first order polynomial equation. Now, to evaluate our model, we would say model.predict, and you give it whatever x's you want. It will return you what the model, how the model projected the x's into the y values, and then this would be our y hat, and then you can get the mean square error calculated from this. You print that, and this would be the results. Now, the mean square error here sounds a little bit gibberish, so let's unpack that here. Let's assume you have a y vector mp.random.rand n for normal, and we'll take, say, 5 values. Now we see y. Okay. Now let's do the same thing with y hat. We see y hat. That is good. Now if I say y minus y hat, this will give me the difference. Then you can wrap this into brackets here, and this is a numpy thing, because y was a numpy and y hat was a numpy. And we want to square this error, so we make it square. And again, you can wrap this, and here you can say mean. So this will give you the mean squared error between y and y hat. And this is what we have here. Familiarize yourself with the way this expression is being done, because you will find it so many times in many machine learning online resources. Alright, so the shape is 1000 by 1, and then 1000. Coefficients, intercept, okay, we have a mean square error relatively high. Now let's plot. To plot the figure, you'll start by making a figure, fig and axis, and then you can scatter the points that you have, say with a black color. That's why we have k here. This x and this y are the ones that we have sliced from x and y at the top. Now we will get the minimum x and minimum y, minimum x and maximum x from this x, and to show you, this is y dot minimum and y dot maximum. These are methods in every numpy array. And from that we will define an x range. This will be the x's that we plot the regression red line against. And this is basically saying I want 1000 points or 1000 values equally distributed or linearly spaced between minimum x and minimum y, and then eventually we'll reshape this into 1000 by 1. So np.len space, if I say give me values from 0 and 1 and give me 5 values, it will give me an array of 5 values scattered between 0 and 1 and equally spaced. Finally, we will plot the predicted value from x range passed into the model against x range itself, and this would have a color red. You can also set the label, give it x for the label, y for the y label, and you can also set the title and say MSE equals MSE. And plot that. You will have here these points. These are the scatter points that we did before, which are here, and the red line is the regression line that our model learned from the data. And this concludes the very first one. This is a very basic introduction. We'll move on to the next one in the next video. Alrighty, so this would be the second notebook. Same things here, nothing really special. We'll just run that. The dataset is also the same. We'll also run that. The pair plot is the same. Actually, in the pair plot, you can have some variations in how you plot this. I need to show you this. So if you replace this with KDE, stands for kernel density estimation. So this would replace the scatter plots with contour plots. This it does take some time to generate, not too much over the scatter plot, but it actually produces a very nice graph like this, and this graph can handle lots of points much better than the scatter plot. Kind of summarizes where the points are scattered in a contour graph. So let's put that to scatter. This contour plot will be very helpful when you work with very large data sets. So if you're working with millions of points, plotting each point out of these millions in a figure will take a lot of memory and a lot of time. Okay, so this is the same dataset that we used before, and this is thanks to the seed that we have set here. So we make sure that we have everything consistent. Now, when we train this model, we will do the train test split, mainly to train on part of the data and test on the other part of the data. So you will import the linear regression model as usual, and then from model selection, you will import the train test split part. This function will take your data, x and y's. You will specify how the ratio of the test data compared to the overall data size, and also a random state here for it's like setting the seed for the random generator when they are doing the train test split. It will return to you x train, y x test, and then y train, y test. This will be your data set that you will train and test on. Now, to train on the data, we'll set this x and this y to x train and y train. We'll choose the x1 feature. Is it the one? Yes. To train on. Always make sure that you check the shape. This is very important, and then you will make your linear regression model, and then you will fit your model on the data that you have from the X train and Y train. And then you will print some statistics or some parameters from the model, and that's it. Notice here that the shape of X and Y has 800 samples. This is 80% of the 1000 samples we generated, and this is because we reserved 20% of the points for the testing here. Now, the other thing we will do as well is we will evaluate our model using the R square score. So to import the R square score, you will import it from sklearn.metrics, and you will use the test X and test Y here. These would be your testing data sets that you will test the model on. The model is already fitted or trained in the previous cell, so now what we need is just to predict what the y values would be, or the y hat would be, if we supply test x in the model.predict. This will be our y hat, and then we get the MSE, or the mean square error, as well. And then to get the R square score, it's just as simple as calling the function R square score, and then give it the original data, and then the estimated, or the y hat data there, and then you print these two. So we can see here this R square is about 92 out of 1, which is not bad. It's really good. Now let's plot it and see how the curves are, how the figures actually plotting. Again, you will generate a figure and an axis from plt.subplot. You will scatter the test data. We need to let's see, this is supposed to be test x, and did we replace this? Yeah, no. And test y there, and we will also make the minimum x and minimum and maximum x taking from the test. We'll generate a new x range from min x and max x here. 1000 elements, will reshape it to 1000 by 1, and then we will plot. And this will be our figure on the test data. And that is it. So any score of any metric that you really want, you will find it in sklearn.metrics. You will also find other functions like for precision, recall, and accuracy, and so on, for the classification part of things. Okay, so that's another step in what we're doing. Now let's move to the third one. Let me just save that for now, and let's move for the third one, and this would be the cross validation. So for the cross validation, again, everything the same, and the very last cell will be the one that is changed. So we have our data generated now, and let's plot let's do the pair plot. I turn off this one just to make it fit here. The difference between turning it on and off is that when it's on, it's more interactive. So if this is in a web page or in a browser, you can actually zoom on things. And let's see the cross validation. This is already here. Let's delete that. Now, to do the cross validation, you will import it from the model selection submodule. It's called cross val score. There is a cross validation function, there are multiple cross validation functions there. Read the documentation, it's very, very useful. Now, what we want is getting the x1. This is the feature that we want to train on, and the y, we'll do the slicing here. We'll make a model, but we will not actually train it. We will make that model, this is an empty model, untrained model. So what we need is to pass this untrained model here. It does not matter if it is a linear regression or a neural network or a tree, decision tree or support vector machine. They all have the same interface of .fit, .predict, .evaluate, and so on. And you give it this untrained model here, you give it the data that you have, the x's, the features, and the y's, which are the targets, and then you specify what scoring you want to do. If you do not specify this, it will actually detect that the model is a regression model from the type of the y and the parameters in the model itself. So it will probably choose R square by default, but it doesn't really hurt if you specify it exactly how you want. And then you would specify the number of folds that you would do the cross validation with. So let's start with, say, 10 folds. And then when you run this, it will run and rerun the model, train it and evaluate it multiple times with the number of folds. This is the leave one out method. And then it will average everything. It will give you for every fold the R square score that came out of this trial. Then you can average them here at the very end, and with that you can display what you display how the cross validation in general works, and whether or not your model slash features are actually performing well or not. So let's run that. Now we asked for 10 folds. These are 10 values, and these are actually 10 R squares for each trial that was done. So if they are 10 folds, it will take 9 to train on and test on the 10th one. If they are, say, hundreds, then, so if we make this 100, it will return 100 trial R square score for the 100 trials. Again, it does this with the leave one out method. It will train on 99 folds and will test on the 10th fold. Now you can see that the score will actually drop when you increase the number of folds. That's because you will have more randomization in the data, and this will give you more insight. But on the other hand, it will take much longer to do a cross validation for this. Bear in mind, this is just linear regression, so it is a very fast method. If you are doing this with say a neural network, this will take much more time. And that is it. In the next video we will talk about more sophisticated code on how to do the regression classification, and we'll also talk about the 2D and 3D plotting of the decision boundary between classes or a 3D regression and so on. I'll see you there.